Hello and welcome to the video on tangents. By the end of this video, you should be able to tell me what a tangent is and describe some of the properties of tangents. A tangent is a line that is in the same plane as a circle and intersects the circle just one time. So I have a picture drawn in here with a couple of tangents on it. Line RS, if I would extend that out, that line would be a tangent to circle P. It hits circle P at just one spot, point R, and that would make point R the point of tangency. That's the one place where the tangent intersects the circle. There is a second tangent to the circle. It is line ST. If I would take ST and extend it out, it only hits that circle one time as well, down here at point T. So ST is also tangent to circle P. One thing that commonly confuses people, they draw something like this and say, hey, isn't that a tangent? It only hits the circle in one spot. Well, no. It would hit the circle in more than one place if I extend the line out. Notice how it hits the circle in two different spots now. So now that we know what a tangent is, we can talk about circles having common tangents. Common tangents are essentially when two circles have the same line as their tangent. These two circles, for example, have multiple common tangents. If I take that line right there, it's basically going to be tangent to both of these circles. It's going to hit them both just at one spot. There's a few other lines that would do the exact same. There's another external tangent to both of these that hits them both once. That looks something like that. Again, they hit both of those circles at just one location. There's also two common internal tangents to these circles. They would look something like this. They hit the circles at just one spot, and one going the other direction. It would hit the circles, again, only at one location. There's a couple of theorems that go along with this particular topic. The first says that in a plane, a line is tangent to a circle if and only if it is perpendicular to the radius drawn to the point of tangency. So what that is saying is that in this circle P, RS is a tangent if and only if angle PRS is 90 degrees. So that's saying if RS is a tangent, then angle PRS has to be 90 degrees. It's also saying that if angle PRS is 90 degrees, then RS has to be a tangent. Again, it says both this if-then statement and its converse because of the if and only if part. Again, it works both ways. And the second theorem here says if two segments from the same common exterior point are tangent to a circle, then those segments have to be congruent to each other. What that's saying is I have two tangents, tangent AC and tangent BC. They're both tangent to the same circle, circle D. The lengths from A to C and the length from B to C, since both of these tangents are coming from that same common exterior point C, that those two tangents have to be congruent to each other. So AC would have to be congruent to BC. One more definition for us here, a circumscribed polygon. A polygon is circumscribed about a circle if every side of the polygon touches the circle at just one spot. Basically, so every side of the polygon is a tangent. An example of something that is a circumscribed polygon is polygon ABCD. Each of these line segments, line segment AB is tangent to the circle. Line segment BC, line segment CD, and line segment DA, each one of those line segments that make up the sides of that polygon are tangent to the circle. It just touches the circle in one spot. An example of something that is not a circumscribed polygon would be polygon WXYZ. Segment WX is tangent to the circle, as is segment WZ and ZY, but the last side over here, YX, is not tangent to the circle. It doesn't touch it at all. Let's try a few examples. The first, assume that the segments that appear to be tangent are, we want to find the missing piece. For problem number 1, if AB is 20 and AC is 15, we're looking for BC. Well, I know that AB here is a tangent because they said anything that looks like a tangent we can assume is. If that is tangent to this circle, then I know that it and the radius going to the point of tangency have to be perpendicular to each other. So basically what I have there is a right triangle. If we have a right triangle, remember we can always use Pythagorean theorem to figure out any of the missing sides if we have 2 out of 3 sides. Since this is 15 and this is 20, I can get my hypotenuse here of x by using Pythagorean theorem. So a squared plus b squared is going to have to equal c squared, which is 15 squared plus 20 squared is equaling to c squared. 15 squared is 225, 20 squared is 400. When I add those together, I get 625 is equal to c squared. And to solve for c, I have to square root. So c is 25. And problem number 2. If EF is 8 and DG is 9, we're trying to find DE. Well, people commonly get this problem wrong because they think this entire side length here is the one that's 9, but if you look carefully, it just said DG was. We need to know how long GF is. Well, any radius of a circle is the same length, so GF is also 8, making DF 9 plus 8, or 17. Now that I know that DF is 17, I can again use the Pythagorean theorem. I know that any tangent is perpendicular to the radius going to the point of tangency, so angle DEF has to be a right angle. If that's a right angle, I know that EF is 8, I'm trying to find the other leg, and my hypotenuse is 17. So once again, Pythagorean theorem. My legs are x and 8, and the hypotenuse is 17, so x squared plus 8 squared is equal to 17 squared. That makes x squared plus 64 equal to 289. Or when I subtract 64 from both sides, I get x squared is 25. When I square root both sides, my other side of this triangle is 15. And 2 more problems. If IH is 12, find IJ. Well, we had a theorem that said 2 tangents going from the same common exterior point have to be congruent to each other. So x is 12. And number 4, if PQ is 6, LM is 2, and MN is 4, we're trying to find PN and the perimeter of triangle PLN. Well, just like the last problem, any 2 tangents from the same common exterior point are congruent to each other. So if MN is 4, then I know NO is 4 as well. And if PQ is 6, I know PO is also 6, making the length of PN down here 10 when I add the 4 and the 6 together. And what's the perimeter? Well, I just have one more piece to figure out here. If LM is 2, then LQ has to be 2 because they're both tangent to the circle and coming from point L. Now to get the perimeter, I just have to add up all my parts. 6 plus 6 plus 2 plus 2 plus 4 plus 4, all add up to 24. That concludes our video on tangents. Have a wonderful day.